Good day, I'm Dr. T and welcome to my office. So today I'd like to talk a little bit about things we can do with nucleic acids. So the technique that revolutionized genetic engineering and all of work with nucleic acids is known as polymerase chain reaction, or PCR. In this case, what we're doing is we're taking the nucleic acid. It needs to be DNA. If you want to work with RNA, you basically have to switch the RNA from RNA to DNA using enzymes, and then you can kick in with the polymerase chain reaction. So what you're going to end up doing is you're going to take your DNA, you're going to heat it up, it's going to split apart, then you use enzymes, and these are typically from extremophiles, so ones that can take the heat, because you need to heat this up enough to split your DNA. That's going to fry most of your enzymes. But in certain enzymes, they can take the heat. So these enzymes then will copy the DNA. They can't do gigantic whole genome things usually, although now that I say that, not saying someone hasn't successfully done that. It's just not typically a viable option. But they're going to be able to copy some of the DNA, or a nice large stretch of it, and then you heat it up again and it splits apart again and they copy it, and then that's during a cool down phase, and you warm it up and it splits apart and they copy it and repeat, and you've got the Xerox machine. And of course, if you've ever seen the parable of the rice on the chessboard, doubling things gets to insane amounts really, really quickly. So we can start out with like literally one strand. So a minuscule amount of DNA, and make it into a rather large amount. It's not economical to make it into ludicrously large amounts. In that case, usually you do PCR to start with, to make it into a modest amount that's enough to work with, and then if you need a lot of it, then you clone that into some kind of bacteria or something, grow the bacteria. That's a lot more economical. But if you need a modest amount, enough to work with, PCR is a great technique, and it's the only real way you're going to go from literally one strand to enough to work with, because one strand is just too small. Now, things we can do with this. One approach we can take is you can take the DNA. Now, you don't just copy any old DNA. You add a primer, because the enzymes that work on this can't just start. They need a starting spot. So they need a short oligomer of DNA to stick on there and then start, and that oligomer is called a primer, and that will be factored into the new DNA strand. So you add primers, and you can pick primers such that they only really stick to kind of one thing. So now you can do is like, do the primers stick? They stick. I made DNA. If I made DNA, that means that the thing the primer sticks to was already in there, so I can use this to detect stuff. This is how we know there's that obnoxious jumping carp in the Great Lakes. We found the DNA for that obnoxious jumping carp in the Great Lakes. To the best of my knowledge, we haven't actually seen the giant carp. Hopefully there's not many, because those are not a good carp. This is also one of the ways that the COVID tests are working. You go from RNA, I believe they get switched over to DNA, and then you do the PCR on this. If you get DNA, now you're able to analyze it, and yeah, you know whether or not you have COVID. Hopefully you don't. Okay, now what else can I do this? This revolutionized forensics as well. So there's a technique that predates PCR, and this is DNA fingerprinting. So you take some DNA and you expose it to some enzymes. And these enzymes are going to slice and dice. But depending on the exact coding of the DNA, depends on exactly where they slice and dice. So now you have all these fragments. You separate out those fragments. You got a couple of ways of doing this. So the traditional way is you take this block of agarose, which is basically seaweed extract, and you use an electric current to run the DNA through it, and it separates it based on size. This then gives you this kind of banding pattern. Now, the banding pattern from my DNA will not be the exact same banding pattern as your DNA, assuming that the technician who ran it was competent and used enough enzymes. Now, with this, we can distinguish, hey, did this DNA come from this person? And if they match, turns out if you use enough enzymes, the chances of them coming from someone, assuming it's not their identical twin, that's not them, are really, really low. And if they don't match, well, it's not them. But in order to do this, you need a fairly decent amount of DNA. Before PCR, you had a little bit, but not enough to work with. After PCR, all of a sudden, you now had enough DNA, even from a few drops of blood, to be able to do DNA fingerprinting. And this led to a whole sweep of reversals of convictions where all of a sudden the person goes like, I'm innocent, I've been saying I'm innocent for 20 years, you're going to execute me in 5 years, please don't do that. Oh, look, we have this new technique. Oh, nope, 1 year blood, we bad, bye. And hopefully that was the case. There were cases where that was discovered after the person was executed, which of course is, horrendous. It's horrendous the wrong person was locked up. But yeah, revolutionized forensics. So yeah, that's a couple of things you can do with it. And actually, one of the newer things is going to be CRISPR and genetic engineering. So if you want to modify that DNA, you got a couple of approaches. You can get a primer, because remember, you have to use those anyways, that almost matches but has a slight change in the primer. And because the primer is incorporated into the new strand, hey, you simply copy the primer over and you now make a new strand with a small mutation. This is fairly common when doing, say, analysis of proteins. You take the genes for the protein, you make a small modification, and then you see what effect that has. And if it breaks the protein, apparently you change something important. If it doesn't break the protein, then it apparently wasn't that important. Of course, now the new thing is CRISPR. In that case, you use some mRNA as a guide, use some enzymes, and then those make the modifications. This is actually a huge rabbit hole, an entire discipline in and of itself. I'm not going to do it justice in a single video, but I hope you've got a taste for this and look forward to seeing you in later videos. With that said, have a wonderful day.